Now we continue to learn chapter 2, determinants. And here we will learn about the properties of determinants. For the determinants, after its definition, we have several questions. The first one, what are the effects of row operations on the determinant? Okay, so before we learn about the three types of row operations, which play important role for solving linear system. So we will consider also what the effect of those row operations will be on the determinant. And the second question is that when is a matrix singular? Right. The third question is how to evaluate the determinant using row operations. So given you an arbitrary n by n matrix, if you want to compute its determinant, so you use the definition like induction, right? It's not easy to compute efficiently because for n by n matrices, you first need to calculate n minus 1 by n minus 1 matrix, the determinant, right? And for n minus 1 by n minus 1 matrix, submatrix, you still need to do cofactor expansion. So n minus 1 of n minus 2 by n minus 2 matrices, you need to compute their determinants. So it's not easy. It's not efficient to compute using definition. So after we know the effect of row operations on the determinant, this will help us to evaluate the determinant using row operations. And then the computation becomes much easier. Okay. And another question is that how about the determinant of the product of two matrices? Okay, so first part. This is a fundamental lemma used in this section. So lemma 2.2.1. Okay, let A be an n by n matrix, a square matrix, if AJK denotes the cofactor of AJK, small AJK, for k varies from 1 to n. See, then we know that this summation AI1 times cofactor AJ1 plus AI2 times cofactor AJ2 plus still plus AIN times its cofactor AJN equals determinant of A if I equals J. If I does not equal to J, then this summation equals 0. So be careful about the left side. See? So here, I may not equal to J. If it's equal to J, if I equals J, then it's just a definition for determinant of A. It's a cofactor expansion along the ith row for A. Right? If I does not equal to G, this summation is 0. So how to prove this? Let's see carefully. If I equals J, then this 1 is just the cofactor expansion of determinant of A along the ith row of A. If I does not equal to J, then we define a new matrix A star as follows. So A star defined in this way. All the other rows comes from the matrix A. We don't change. Only the jth row. The jth row now we change to the ith row. Before A in A is AJ1, AJ2 till AJN. Now it's AI1, AI2 till AIN. So for this matrix we constructed, since two rows of A star are the same, we know determinant of A star equals 0. So this is a property of determinant. If you find two rows are same, two rows are identical, then the determinant equals 0. Writing the cofactor expansion of this determinant of A star along its jth row, you will get determinant of A star equals 0 because it has two identical rows, which equals AI1 here, the first entry in the jth row, times its cofactor A star J1 plus AI2. Okay, the second entry in the J0 of A star times its cofactor A star J2 plus TL plus AIN, the last entry in the J0 of A star times its cofactor A star JN. Okay, and then think about A star J1, A star J2 till A star JN. They are equal to AJ1, AJ2 till AJN correspondingly. Why? So this is important, right? Because A star J1 equals a sign times is a submatrix which deleting the J row, right? Deleting the entry in the J row and the first column of A star. If you're deleting this row and this column, you will get the same submatrix. If here is a matrix A, you deleting its J row and the first column, you get the same submatrix. And the position to find its sign minus or plus, right? Also comes from the position. They are same. So here, it also equals AI1 times AJ1 plus TL plus AIN times AJN. So we get its conclusion here in 1.